I did the heat map, pair plot, and part of training the model for this project.
My name is Alex Galloway. I did the training the model and part of the input functions.
Hi, I'm Jack Lawson, and I did the literary research and also helped remove outliers from the data frame. So getting into the literary research, what this data frame is a conglomerate of around 6 or 7 years or 5 years of data from a combined cycle power plant and how it generates electricity. A little bit about a combined cycle power plant is it is an advanced system that utilizes both a gas turbine cycle known as the Brayton cycle and a steam turbine cycle known as the Rankine cycle to generate electricity. So in the first stage of a CCPP, air enters the gas turbine cycle and is combined with fuel, which is then combusted to create a high pressure and high temperature gas that generates electricity in the gas turbine. And then after that, the excess hot gases that pass through this they pass through the steam turbine cycle, specifically something called the heat recovery steam generator that captures the wasted heat from the gas turbine to produce steam. This steam powers the steam cycle and allows it to produce even more electricity. And using both of these cycles, the gas and the steam cycle, it allows the CCPP to output a higher thermal energy and efficiency than single cycle power plants. And how does it do this? The main benefit to a combined cycle power plant is that it can put the excess heat that would normally be wasted in a single cycle power plant to use. It is used to power the steam turbine, while otherwise it would be lost to the environment in a single cycle power plant. This allows the CCPP to have a much higher electric energy yield with the same amount of fuel being used. Another advantage of a CCPP over a single cycle power plant is their ability to emit fewer greenhouse gases compared to single cycle. Since they extract more energy from the fuel and have more efficiency, they burn less fuel over time to produce the same amount of electricity. So if in a single cycle power plant you need to use a lot more fuel to produce the same amount of electricity a combined cycle power plant would. Additionally, the increased efficiency of the CCPP reduces fuel costs, and because less fuel is required for the same energy output, it costs a lot less to run a single cycle power plant. So, and they also, like I said earlier, they operate with a lot lower efficiency, meaning they consume way more fuel, leading to higher operating costs. By combining these benefits, combined cycle power plants provide a much more cost-effective, efficient, and environmentally friendly solution for electricity generation. Moving on to the database described, this data set that we used to develop our regression models is from a combined power plants or combined cycle power plant operating under the full load conditions of 6 years from 2006 to 2011. It has around 9,500 data points consisting of 5 different variables, starting with AT with the average temperature measured in Celsius ranging from about 1.8 to 37, and then V, exhaust vacuum, is measured in centimeters of mercury ranging from about 25 centimeters of mercury to around 81. Next, AP, or ambient pressure, is measured in millibars ranging from around 990 to 1030 millibars. Next, relative humidity, or RH, measured as a percentage from all the way from 25 to 100%. And finally, the last variable is a prediction of the net hourly energy output using the previous 4 variables represented as EP, measured in megawatts. It ranges from around 420 megawatts to 495 megawatts. All variables are real and continuous in this model, making it ideal for regression models.
The code, we import all the modules we need in the project, and then we create a variable that reads the data file that we have. We then use the describe function to further understand our data, and then we use info to check if there's any nulls. After that, we have a few if statements, kind of, with the dot drop method to remove some outliers from our data to make the data more accurate. And then we use a heat map to see what parts of our data have the highest correlation. As we can see, the AT and PE have the highest correlation because they're the closest to 1. However, it's also negative, so it's also a negative correlation. And with a dot pair plot, we can see every graph and how they look. Looking at AT and PV, we can see that it's the most linear line, which makes sense because it's also the most correlated. So for one of our models, we ended up using AT and PE because they're the most correlated. So here we used linear regression and we trained the model to give us the coefficient and intercept so that we can use that in a formula to be able to predict the output given an input.
Continuing from Sean's part, I did the second model, which is the full model with all 4 inputs. As you can see here, we input all 4 variables and we assign them to the training variables. We fit the regressor and we assign the variables for the coefficient and the intercept. And we print these so we can see it. And I create a lambda function so we can easily input all 4 variables with just one function with 4 inputs. I'm going to explain how the input block works. So the user is given a choice to input a number, which is 1 or 2. So I'll input 1, and that gives the user a choice to pick a number for AT. So for example, I'll input 23.25, and that gives us 446.64. So that's the output for model 1 because it only has 1 input, which is AT. If I choose model 2, I get a choice for 4 inputs. So I'll input 23.25, 71.29, 1008.05, 71.36. And that gives us an output of 443.27. And here I'll input all of the test variables we were given. And that gave us 466.98. And now I'll input the third set. And that gave us 461.4. And now I'll input the fourth set. And that gave us 477.55. And now I'll input the last set. And that gave us 469.15. And after every time we input for Model 2, it inputs the variables we were all given back into the original data frame so that the model can update based on our inputs. So here I create an example scatter plot of the Model 1, which shows the linear regression between the AT input and the PE output, which has the intercept, and the coefficient. I originally intended to do it for Model 2, but I can't do that because that would need a 5D graph. And here I have I have a bunch of variables that we can give, or a bunch of arrays that we can give into the model all at once and get a bunch of PE outputs.
Finally, we look at the root mean squared error, which we see is about 4.34, and that tells us about how off or how much the error of our model might be. So it's not completely accurate, but it is pretty accurate to what we need it to be.
Well, this project was fun to work on. We worked well together as a group. It was very challenging. It took a little bit to get a good understanding of what we were doing, but once we did, we really took off and worked well together, and we are very impressed with our final results. Thank you for giving us this opportunity, and thank you for teaching us this semester.